Alright everyone, let's go ahead and get started. So can I get everyone's eyes up here? Alright, so on the agenda for today, okay, when you get to your chair, Brian, I need you up here. Alright everyone, so on the agenda for today is that we are going to start reviewing. So yesterday we covered the last topic that we were going to cover for Unit 3, which was energy and power. So we finished up with all of the new things that we are going to learn, and today we're going to be starting off our review. So today we're going to start reviewing just the big topics of energy and momentum, and then we'll narrow it a little bit further and do collisions. You will have a practice exam on Thursday. It will be graded as usual, and you have your unit exam on Tuesday. Again, as a reminder, if you cannot make it next Tuesday, if you can't make it a week from now, you have to let me know so I can make arrangements for you to take it this Friday. If you don't do it in these 2 weeks, it will be a 5th week. So you have to do it in these 2 weeks. All right, are there any questions about that? All right, if not, let's go ahead and get started. So, as usual, we're going to be following the same format for the review, which is that we're going to start off trying to come up with just the big key points of the topic. So every time we do a review, we start off trying to come up with everything that we remember, so we know everything that we know and everything that we need to study. So I'm going to go ahead and give you 8 minutes with your table to try and come up with as many of these key points as possible. If you forget something, you don't know what impulse is, you have your reference sheets at your tables to help you look through and try to remember some of those topics. So if you forget anything, look at the reference sheet, ask somebody at your table, so you can try to fill out as much of this as possible. The more you fill out, the more you know, the less you actually need to study. So let's go ahead and take 8 minutes. Your time starts now.
Alright, so we're kinetic. Gravitational. And what is it?
So kinetic is right. Static is close. Static. So you're missing one more. Not static. What is the S sign? Oh.
That's UG, that's US. Gravitational is UG. You was still gonna write it down though? Exactly. But I was so who's worse than you, because you're following. Exactly. That's why you're getting something.
Alright, we are 2 minutes in. We should be moving on to the second box. So we should be on conservation of energy.
Sorry about that. I realized I had one extra. I don't think I put one in here.
If I turn it down, I don't know what's wrong with it. It doesn't change. So the law of conservation of energy is that one by energy. There we go. Got it. This bit is right.
What is it? Conservation of energy. Keeping initial.
Alright, we're about halfway through, 4 minutes in. Remember, try to fill out as much as possible and use your reference sheets if you get stuck somewhere.
We don't say the same.
Look at your reference sheets, you got them there. So those are things you don't need to remember. I meant more like two of them on your record.
That's only because it comes out February. It was like red. What?
How are we doing?
Then you gotta put change, leave.
Alright, that's good.
Equals work and it states.
I'm not kidding. Because I was already eating.
Conservative energy. But that doesn't make sense. It will stay the same from finish to end. We have 2 more minutes. This table is nearly done.
W equals right here. KD.
The idea of knowing what the equations are isn't that you have them memorized, it's that you can find them. But in an exam, you're not like sitting there thinking, where is it, where is it? So when you get to the exam, you know
Wait, what do you mean? What are 2 ways to calculate work? By using this
No, but give me the equation. Using this is very big. Like, you say this, I'm like, the
Why just put down for another one?
Slightly under a minute. Make sure you fill out as much as possible.
Isn't it the one of the KD? Remember the 1/2 KD? Yeah.
For some reason, I don't feel like that's a part of the
What?
Yes. There you go. You have about 20 seconds remaining. Try to fill out one last box. What? Yeah.
Boys, you fine?
That's what D times please. E equals momentum. Look at input.
Momentum is.
So look at. Alright, everybody, time is up in 3, 2, and 1. Let's bring it back over here. Alright, Camilo. What are the 3 types of energy?
Kinetic, gravitational potential, and elastic.
Kinetic, gravitational potential, and elastic potential. So these are the 3 different kinds of energy that you can have. If you look at your keys, they're written there in more detail. So as we're going, if you miss something that I write on the board, you can go ahead and fill it in from over there. So remember that you always have 3 different kinds of energy that something can have. This one can be anything, and these 2 are potential energy. So potential energy can only be in a system. So those are 3 kinds of energy that you need to know, because when we start off with this unit, we start off with energy. So it's one of the most important things that we've done so far. So going on from energy, we have this topic called conservation of energy. So yes, what does conservation mean when something is conserved? Or it doesn't change. Conservation means that something is constant. It's not changing at all. When energy is conserved, that means that the total energy is going to stay the same in a closed system. So you have to remember that the total energy stays the same. The second bit is a little bit more tricky, which is how does this apply to problems? So when you have a problem about energy changes, a lot of the time it's talking about conservation. Because energy can change form, it can go from kinetic to elastic to potential. But it will always, in a system, stay the same. The total will always be the same. So this is actually an equation that's not on the reference sheet, which says that the E initial, the total energy in the beginning, is equal to the total energy at the end. So this is a pretty important equation that is not on your reference sheet. So this is the one that has to do with energy. And then we also did conservation of momentum. So conservation of momentum is also pretty similar and also not on your reference sheet. So if you're talking about momentum, that's the one that says P1 plus P2 equals P1 dash plus P2 dash. So both of these equations are pretty similar because what they're telling you is that the total of something is staying the same. In this case, your total energy stays the same. In this case, your total momentum stays the same. This is why conservation laws are pretty similar, because all they're talking about is one thing that is always going to stay the same. So when you get to an exam, if you have a question about either of these things, these are two equations that you need to know that are not on your reference sheets. So this is something pretty important that you need to know. All right, is it okay if I change the page?
Yeah.
All right, let's take about 5 more seconds to finish writing that up. You can stand if it's hard to see. Got it? Okay. Let's keep moving. All right, so 2 ways to calculate work. The FD one? You're right. This is one of the first equations that you see on your reference sheet that tells you about work. So on your reference sheet, the bottom 2 equations in the box that we've been looking at, those are the ones about work. So over here, you don't need to memorize these, but you need to be able to find them quickly. In an exam, you want to know where all your equations are, so you're not wasting time trying to find an equation, and you have as much time as possible to actually do the work. So if any of you need like a paper reference sheet that you want to look at, I've got some extras, and you can ask me after class, and I'll give you one. So you can take it home and you can study it, so you know like where everything is. All right, and the second way to find work. So the second way to find work is actually hidden in your power equation. So your power equation deals with the work done on an object, but sometimes you can work backward and find the work done on an object. So these are your 2 ways to find the work done on an object. Find capital W. All right, this here was I think one of the most tricky ones, because also on your common assessment there was a question about this, and a lot of people struggled with that question. So I really wanted us to focus on this one, because I don't think anybody got this question right, which means that I probably did not teach this right, or it's been a while since we covered this. So the area under a force time graph. So a force time graph is a graph that has force on the y-axis, and it has time on the x-axis. The question is asking, what does the area under the graph mean? So what would this area be? So the first thing that you want to know about the area under a graph is that it gives you the multiple of the axis. So any area that you find is going to give you your y-axis times your x-axis. So when you multiply those 2 things, you're finding their product. That's smart. So when you multiply those 2 things, you're finding their product. So your area here is your force into your time. And if you look on your reference sheet, there's an equation that has force multiplied by time, something that we've been studying. So somebody try to find me that equation, something that has force into time. Impulse. This is actually your impulse equation, because your impulse equation has force into time. So the area of a force time graph is your impulse, because it's force into time, which is the same as your impulse. This J here, that's your impulse, or your change in momentum. So if you ever see a graph like that with force and time, or with anything on the axis at all, you want to see what's their multiple. Because when you find the area of something, you're multiplying 2 things, right? You're multiplying base times height, which gives you the area. So this is a little bit of a tricky one, and we are going to practice this if this is confusing to you, because I saw that a lot of people are struggling with this concept. All right, nearly there. How do we find momentum? P equals mv. Shortest equation that we learned. P equals mv. It's still P, that's your momentum. 2 ways to find impulse. So I actually kind of gave it away over there. So the 2 ways that you can find impulse are either a change in momentum or force into time. So if you write this out, your impulse is either delta P, which is P final minus P initial, or it's your convert force into time. Again, not something that you need to memorize, but something that you want to be able to find. When a question says, what is impulse? You want to know impulse is J, so that when you look at your reference sheet, you can find it. You don't got to memorize the formula, but you have to be able to understand what a question means when it's asking for impulse. So if you're somebody who gets mixed up in the variables, you want to practice that. Alright, is it okay if I change the page? Okay. Oh, I forgot about the last two blocks. Oh, wait, one's repeated, so really just the last one. Alright, how does the time affect the force on an object for a given impulse? So, did anybody come up with this one? How does the time affect the force? Yes, Jordan. That is exactly right. As your time increases, your force decreases. So if you think back, this is quite a while ago, to the video that we saw about the egg, when the man threw the egg at the wall and the egg shattered. Do you remember this?
Yes.
Okay. So when the man threw the egg at the wall, the egg shattered, right? Because it takes a split second for it to hit the wall and then break apart. So there's very little time, which means that there has to be a lot of force. But when the man threw the egg at the bed sheet, it took a lot longer for the egg to slow down. So the bed sheet moved with it, right? So it takes so much longer for the egg to slow down. So because the time was much longer, the force was much smaller. And since the force was smaller, the egg didn't break. So every time you have a big force, like with the wall, you have a little t. And every time you have a little force, like with the bed sheet, that means you have a big T. So for the same impulse, they change inversely. They're inversely proportional. When one goes up, the other goes down. And I think this is just a repeat of the same box for some reason. So we're actually done. These are like the big concepts that we need to know. So now that you fill this sheet out, this is going to be a review sheet. So when you go home, if you still don't understand any of these concepts, you're going to have this to review. So now we're going to go ahead and move on to our practice questions. So I'm going to give us 2 minutes to do question 3, and then I'm going to go over, just so that we can get a feel for what these questions are like, and then we're going to move to independent work. So let's take 2 minutes with our tables to work on question 3. 2 minutes, let's get started. If there's anything I said that you don't understand, your key is like stuff in more detail. No, it's not the social one. Also, I only have those somebody brought them for me, so blame them for all. How do you do question 3?
Just see.
We have about 1 more minute to finish on question 3. Let me know if you have any questions. Oh, yes.
Yeah, but if it increases your and it was a 1 and 1
How do you do with question 3? Did you get double? Okay, so this is actually pretty complicated. This thinks that the velocity doubles, so the height is velocity power.
yeah.
Alright, everybody. So, if you were struggling with question 3, I'm going to go ahead and go over it on the board. Everybody else, you can move on to the next page. So, for these questions, I would like you to work independently, but every time you finish a page, you can go ahead and check your work with your table. So every time you finish a page, you can either check your work with a partner or with your whole table. So try to do the questions independently, and then you can check in to see what you got. And if you get stuck, you have keys, and you can ask me for help. All right. So again, if you're struggling with question 3, let's go ahead and go over that over here. So in question 3, you've got an object with a velocity v, and then your velocity changes to 2v. So this is a change problem. So in a change problem, you want to start off with the original equation, which is k equals 1/2 mv squared. And then you want to find how did it change. So for your change in k, you got to figure out what is changing. So over here, Giovanni, what's changing? Sorry. Huh? The velocity. The velocity is changing, right? This is the only thing that is going to change. Your 1/2 is going to stay the same, and your m is going to stay the same. So anything that stays the same turns into a 1. This 1 basically means no change, like it was being multiplied by 1. And then over here, your velocity changes by 2. So I'm going to put in a 2. Once you have those plugged in, you can go ahead and multiply that out, and you get 4. So that basically meant that your kinetic energy was being multiplied by 4. Another way to look at it is to look at the equation, see how much does it count. So your velocity counts twice. Because if you were to write this out, you would write this out as v into v. So your velocity is going to count twice. So any change in your velocity is also going to count twice. If it was 3 velocities, it will count 3 times. Right? If it was 4 velocities, it will count 4 times. Any change that's happening is going to happen twice because it's happening to your velocity. So you want to plug it in and then square it. So if you just write kinetic energy doubles, because velocity doubles, you're going to be off because you forgot that it was counting 2 times. All right, let's go ahead and keep moving. We can turn the page. Ignore that. All right, so let's start off with what's happening here. So over here, we've got the new roller coaster, and it goes down, right? So the roller coaster moves, and it says it's frictionless. So when it says it's frictionless, it's actually in a little clue that says that there's no energy loss. And then the motionless is like keeping all of this energy, right? All of the energy. So this is an energy conservation. So based on that, start eliminating. Which one cannot be eliminated? So this one, so you got 1, 2, 3, 4, 5. Yeah, so that one you cannot possibly be, right? So we're going to eliminate that. Then figure out, over here, you've got the information for which point. What point is that? Over here, right? And then it's asking, I'll tell you what's happening here. It's asking you so you already know total energy is going to stay the same. Then we got to figure out what's going to happen to your potential and your kinetic. So I know about potential energy. Think about that. You start eliminating. So look at the equation. What do they when to use the height. All right. So there's 2 that red is 2. So over here, draw the picture. What happens in the board? Yeah. The ball starts off over here, it lets it go. It's asking you what's happening to it in the middle. But it's still falling, but it's still in the air as well. So when you start off, what kind of energy will you have when you're just holding the ball? When you're just holding right? You just have gravitation. Then you let it go. Over here. Still falling, but this is kind of like where you want your snack. So over here, what kind of energy? And then again, so your initial energy is totally just
You don't get it? No. You don't get it? So your girl make you me miro gorda. Y tú me dices, gordita me la pone. Okay, you got it.
Okay, so
But I'm not what? You get it?
that one? Which one did you think it would be? Okay, so there's one very important distinction. Okay, so let's say the ball starts what's right there for formula? So it's actually the first one you stand up. The first thing you want to check is your approach. So it's like the first one.
Yes, I got it. I got it.
What formula?
No, I need to say
What
gordita me la
what
pone.
happens the most? What keeping it there?
I got it the first
So
time.
what? Okay, but what formula will you use? That's it's not how you use. So total mechanical energy is just like grip and up. So this is actually a concept that we don't really cover anymore. The question was really about how long What energy do you use whenever?
So the total energy that it has, so think of this as just like the total energy. So you don't have to worry about elastic because it's not being stretched or anything. It's just like its total energy.
Well, there is
What's happening in the
we have two left.
what's happening.
Static
Then
and
it's
kinetic.
what's going to happen at point.
So which other one?
To start off with what you know about
So you're
what
gonna
has
use
here and what you think should be happening.
Sorry. If you were here, we should say it. So it's
So what do you know about
G
total
equals
energy?
K plus UT. Does that make sense? Since it's
Oh, you mean?
Or anything. What do we know about the